My plan tonight is to give you a little background, starting in the space age of what we've been finding out, and then why there's a renewed interest to go back to the moon, or as we like to say, to go forward to the moon. You know, it's really an exciting time for us, and it begins in the early part of the space age. We had many missions that we started to fly towards the moon in many different configurations. There were flybys. We tried to orbit. We tried to land. And we made many measurements. This is an overview based on those missions up to about 1976. 21 of these missions NASA did to get ready to put humans down on the surface. In many ways, you may be familiar with Star Trek, but NASA doesn't do Star Trek. It's not go where no human has gone before. You know, we don't take that philosophy. We actually study the environment we're going to move into, and then we move into it. That's currently happening at Mars. We have a fabulous set of missions, international missions from ESA and also the Indian Space Agency are orbiting Mars right now. Also, the Russians are working with the European Space Agency, in addition to the NASA missions and the rovers. So this is just a spectacular time. So let me take you back to the Apollo, the first landing on the moon by Buzz Aldrin and Neil Armstrong, along with Mike Collins orbiting the moon, launched on a Saturn V on July 16, 50 years ago, okay, 1969. So I, as a young adolescent, had an opportunity to observe this. Perhaps some in the audience has. But many of you, as I look out, probably aren't very familiar with that personal experience. But I want to tell you about how exciting and unbelievable it was in so many ways. The first landing on the moon occurred then on July 20th, 50 years ago. And so we're celebrating that. Neil Armstrong was the first to step down. One small step for man, one giant leap for mankind. And in their mind, it was all about the fact that the human race has left the gravitational bounds of the Earth and moved into space, moved into a new planetary object, the moon. Once the two got on the surface, they began to deploy a variety of instruments. The instrument that you see in front of us is a seismic instrument, but right behind that is another fascinating instrument. This is about 1.5 by 1.5 feet array of light reflecting lenses, and we're going to shoot lasers off these and time the light to the moon, reflecting off this array and back to the Earth. And because we know how fast light travels, we are then able to make the first measurement accurately within a few wavelengths of light to the distance of the moon. And we have been doing it every year for the last 50 years. Okay? And there's a reason why we're doing that I'll tell you about. After this mission, there were several others. Here are the 6 successful lunar missions. Of course, Apollo 13 was famous in another way, didn't have the opportunity to land and rove on the moon, but indeed was a spectacular success for NASA and forced NASA to think in different ways. You know, failure wasn't an option. We had to bring these men back. And so from then on, we began the process of, as we go out into space, looking for everything that could go wrong and creating contingency plans. And that has served us well. And we're going to continue to do that. Each and every space mission that we do, we learn something from that. And we have to fold that into the next series of things. As you can see, all these missions landed close to the equatorial area of the moon and on the near side of the moon. Of course, the moon has two sides, the near side and the far side. Some people call it the dark side of the moon, the far side, but that's incorrect. And that is because only half of the moon is lit and half of the moon is dark. And so when we see a dark area on the moon, there's a light lit area on the moon on the back, okay, on that far side. And so indeed, that's an exciting aspect of a planetary surface we haven't been. In many ways, we know more about the surface of Venus than we do the far side of the moon because we haven't landed on it. Now, only Chinese have landed on it recently and have began to do some science there. Now, this near side of the moon has many features associated with it. These dark areas are called mare, and there's highlands and all sorts of exciting things. And these astronauts went and collected material. They collected, ground up soil. We call that regolith. This comes from impacts that have occurred on the moon, busting up rocks, and there's pieces of material all over the place. So they collected about 850 pounds of rocks and brought them back. And we've been analyzing them ever since. And we're finding some astounding things. In fact, here's one of the laboratories that we use to what we call curate these samples. These samples are brought back at the Johnson Space Center. And in there, we're teasing out all kinds of fascinating things. One of the first things we found out was actually the moon was very much like the Earth. The mineralogy was very much like the Earth. And most recently, embedded in a moon rock, as shown right here, is this particular area is not from the moon. It's actually a rock from the Earth. Now, this is really exciting. How could a rock from the Earth get to the moon? Well, just like rocks from the moon get to the Earth, it comes from impacts. And when we look at the moon and we see these massive craters, early on, planetary scientists thought that they were caldera and that the moon was very volcanically active. Well, yes, the moon is volcanically active, but the craters are not from volcanoes. They are from impacts. We also learned from the rocks that these impacts, for every one on the moon, there's 20 here on Earth. 20. So where are they? Where are these impacts? Well, because the Earth has an atmosphere, plate tectonics, an ocean, its land formation has changed enormously. The oldest rock we can get here on Earth is about 3.8 billion years old. We find them in Australia and some in Greenland. But this rock that's embedded in material that is on the moon that the astronauts brought back is older than 3.8 billion years. It's more like 4 billion years old. And because the moon doesn't have a biosphere, plate tectonics, an ocean, or an atmosphere, that material has stayed pristine since it was made 4 billion years ago. So the rocks that we brought back from the moon allow us to date the age of the Earth. We can't do that from Earth rocks. And we find that the Earth and the moon are about 4.6 billion years old. Okay? So this is one of the exciting discoveries that indeed has come out from the Apollos. And oh, by the way, what we're finding from the retroreflectors is that the moon is moving away from the Earth about 1.5 inches a year. And it's done that over the last 50 years. And of course, it's done that over the last 4.5 billion years since it was created. Now, if we move into the modern era, after about 76, there was sort of a hiatus. And that sometimes happens in science. It happened at Mars, happened at the moon, and for a variety of reasons. And since 76 was the last mission, it was a Soviet mission that landed on the surface of the moon, you have to go into the 90s before we start picking up the interest going back to the moon. Some of that is because it takes many years, maybe a decade or more, to understand the material, understand the data that you've acquired from these missions, to really determine what to do next. And what we're finding out from this set of missions in this last 30 or so years, this decade was spectacular in robotic missions, like the Lunar Reconnaissance Orbiter, which is still operating. The Chinese now have stepped up and have actually landed a number of things on the moon. The Japanese have been also launching things to the moon. And collectively, we're studying the moon in new and different ways. So let me tell you a little bit about this era. Since 1990, what have we learned? Well, we're able to really, in high resolution, examine the surface of the moon. So this is data from the Lunar Reconnaissance Orbiter, and it's split up in the near side and the far side. And so when you look at the near side and the far side in these images, this is in light that you can see, you recognize immediately how different they are. You see the Mare, and the Mare are lava material. We call it basalt, basaltic material. This lava has flowed into a massive impact region. So each of these mare show, they're roundish. That's an impact that forms a hole we call a basin, and then lava flows into it. On the far side, where are the mare? The mare doesn't seem to be very prevalent on that far side. And any origin of the moon has to take all these facts into account. If we take another look at the moon, and we can see, now this is done in altitude, where we've colored the data in terms of the reds and the whites being the highlands, and the blues and the purples the low features. And so what you see is the highest points on the moon are on that far side, or on the side that we don't see regularly. And the lows are indeed on the near side, but also on the far side. In fact, there's one particular area. It's right here. It's called the South Pole Aiken Basin, and it is an impact. And this was an enormous impact that blew away a huge amount of lunar material. We believe it blew away most of the crust of the moon. Now, from a planetary science perspective, when we put planets together, we have cores, where all the heavy materials sink, like the iron, the nickel. And then we have a mantle, and then we have a crust. We cannot get to the mantle of our Earth, and yet under pressure, new minerals, new mineralogy of the materials are created under high pressures in the mantle. Here is mantle material exposed on the far side of the moon that will teach us about how the Earth is put together. So this is one of the huge important reasons we want to go back to the moon, is to really understand how terrestrial-like planets are put together, and that, of course, includes the moon. The difference in the highs and the lows between the white and these purplish areas in this image is about 13 or 14 kilometers. That's greater than the distance between Mount Everest and the Marianas Trench in the ocean. So these huge landform variations on the moon are greater than here on the Earth, and they must take that into account as we try to understand how the moon came into being. Also, this particular set of data is all about the size of the crust. And when we look at the near side, compare it against the far side, we see the crust on the far side is thicker. And that thick crust may inhibit magma coming up and filling in impacts in these basins. That may be one of the rationale why we don't see magma flowing into these regions, except why isn't the South Pole Aiken Basin a mare? All right? And so we also believe the gravitational lock between the Earth and the moon, where the moon presents only one side, as a gravitational pull and effect on the lava as it bubbles up. And maybe that's an explanation of why the South Pole Aiken Basin hasn't been filled in. So these are some of the exciting things that have occurred in that second era of lunar exploration. Enough for us to put together a new picture on how the moon and the Earth were created in the configuration that we have today. Early on, there were many theories. Maybe the moon was formed somewhere, and as it came close to the Earth, we captured it. Well, that might be okay if it's a small object, but the moon is huge. All right? We're almost like a binary system. The center of mass between the moon and the Earth that we move around is inside the Earth, and so the moon does indeed look like it goes around the Earth, but it is still a very large moon, larger than any other moon linked to a terrestrial planet. Now, there are larger moons in the solar system, but they are in the outer part of the solar system, and they're connected with the gas giants. So, dynamically, we couldn't capture the moon, and so that was a problem. There are other theories that we went through, and we methodically knocked them off. And then our computers were so good in 2000, early 2000, that we then began to model how the moon might be created. Now, we have to be able to accommodate all that we know about the moon. And one of the leading theories at this time was the moon and Earth were created from a massive collision of the early Earth and another object that was also accreting in the orbit of the Earth that we attracted and brought in. Now, we call that object Theia. And so Theia, we believe then, about the size of Mars, hit the Earth, and the end result turns out to be the moon and the Earth. So that particular theory we could test with computers. And so what you see on the right-hand side is indeed the computer model of all the points that we're going to track in a dynamic impact. And so here is the simulation. The impact occurs. The attraction of the Earth will bring a significant amount of material back. What just came back was the core of Theia, also impacting the Earth. And then we see a debris field, set of material that is flowing around the Earth. Now, one of the important aspects of Theia losing its core to the Earth comes from the seismic measurements we've made of the moon that seem to indicate the core of the moon is much smaller than it should be. And so it has lost a significant amount of this core material, and of course it can do that from impacts. Now, if we step back a little further from the Earth and look down on what's happening, there's a region around the Earth, it's called the Roche limit, for which anything that reforms inside of the Roche limit will have huge gravity perturbations, and it will be pulled apart. The gravity on the closest side will be more than the furthest side, and so that's how that material gets pulled apart. But beyond the Roche limit, you actually can accrete something. And so what's happened then at the end of the impact and outside the Roche limit, two objects form: the Earth and the Moon. Now, fortunately, you can't see all of the Moon in this particular example, but there's one important thing to note. It's really close to the Earth. Okay. In fact, if you were to go out at night during this time, 4.55 billion years ago, and look up, the moon would be 16 times bigger than it is today. I mean, it would dominate the sky. It would be absolutely enormous. And because it's so close to the Earth, the gravitational pull on the moon is such that it locks it to one side, always pointing to Earth. Okay? And like a ballerina, as she spins and pulls her arms out, and the moon is moving away 1.5 inches a year, ever since this occurred, the day on the Earth slows down, just like the ballerina does. And so at the end of this impact, the Earth must have a day that's about 5 hours long. And the end result of this is where the moon is 60 Earth radii away, moving continually away from the Earth at 1.5 inches a year, but still maintaining that tidal lock with a smaller core, made at the same time consistent with the Apollo samples. And so now this is our leading theory. And so, as an overview, here you see the size of the moon relative to today, and its motion then gives us the day of 24 hours. Another really important event occurs in this impact and reformation into these two objects, and that is their rotational axis becomes locked also. Now, why is that important? Well, when planets are formed, even though we think them of a nice spherical nature, their gravity is actually very lumpy. There are some places with higher mass than others, and if you step back and you looked at the Earth from a gravity point of view, it would look like a pear, not like a cherry or an apple. And that mass difference means that the sun's pull on the Earth, even though it's spinning, will force that axis to spin around over time and even maybe lay down, changing the climate on Earth in enormous ways. But with the stability of our axis at 23 degrees, with the moon locking us and keeping it in that direction, the climate has actually been modified significantly from what it would be if we had these nutations going on. So the moon has actually helped provide an environment for us to evolve in. What about the far side of the moon? How come it's so much thicker? Well, the concept is, after the cloud came together and we have a moon, what about another moon? Maybe two objects were created, and those two objects collided and formed that far side of the moon. Doesn't have to be as big as the initial impactor, but indeed that's one of the prevailing theories that we have. There's another theory, and that is when the Earth formed or reformed from this impact and the moon was created, the Earth was enormously hot, and it heated the front side of the moon, that near side. And in fact, that heat released atmospheric material that's trapped inside the moon. That would be water, carbon dioxide, and carbon monoxide, and ammonia, sorry, etc. And so those volatiles would then leak out, and what would happen? Well, they would move in an atmosphere to the other side of the moon. And maybe that indeed is what was happening. So that's an alternate theory. I haven't quite figured out which one, but we'd like to go back to the moon and verify that and figure out what it is. Now, one of the things that's important about going back to the moon is it allows us to create a chronometer of events that occurred throughout the solar system. So we see two areas, an old lunar terrain and a new lunar terrain. And how do we tell the difference? Well, one has a lot of craters and one has few craters. What does that mean? Well, that means the area with a few craters must have been resurfaced at a particular time. And then the new craters that occurred after that resurfacing. Okay? This is why the Mare is so important. They are not heavily cratered. They're very important for us to go there, collect rocks, and bring them back and date them. Now, we use that same basic idea to date all kinds of things in the solar system. The moons of other planets, Mars. And it's all about knowing the cratering rate over time and the size of these craters, and we can create a time evolution of our solar system. Now, I have some of that correct, but we need to go back and obtain additional samples and date them to make sure we can create the right chronometer. Well, what else about the moon? This is the moon observed in the infrared, which you can't see, but we've colored it based on that spectrum in light that you can see. And what you find out is that the moon is really heterogeneous in color. These are enormous differences in color across the moon, which means there's enormous differences in the mineralogy, which means material that's hit the moon, laying on the surface, creating these different colors, was put together at a different place in the solar system and was transported to the moon. So, where did they come from? What is that material? What do we need to know about those to really get the history of it correct? So now when we look at the moon, we can look at it with the concept of age dating, okay? And so here's our best guess, based on the samples we brought back from the moon, based on getting the ages of many of these places correct, guessing the ages of the other places, although we don't have dates, we have this impact chronometer idea, okay? And so what we find is these big impacts in particular have a range of dates. These huge basins in particular are younger than the rest. Now, how does that go? Why is there a huge amount of bombardment going on the moon, creating huge basins 800 million years after it's made? How does that happen? Now, these objects were made elsewhere in the solar system and flung towards the moon. Something happened in the outer reaches of our solar system that we're just now getting a glimpse of. And now we begin a separate part of solar system research in the hands of the modelers. In early 2000, as I said, computer technology allowed us to really study how the Earth and Moon came together. And we also then studied about the rest of the solar system. And there was a conference in Nice, France, where all the big modelers came to discuss how they put the solar system together, how all the giant planets were created, all the terrestrial planets, and to really understand that time scale. So each and every one of them got up and they talked about what they could do and what they couldn't do. And none of them could form several of these outer planet giant gas giants. Couldn't do it. They ran their models for 4 billion years and they couldn't form Uranus and Neptune. That was a problem. None of them could do it. So they went out that night in Nice, France, went to a nice French restaurant, poured the wine, and as the evening went on, they discussed what physics are we missing. And everyone's models had what looked like all the right physics or emphasized the most important physics, and yet they couldn't come to it. And one of them said, well, let's sort of forget about our own solar system. Let's form anything we can. So what do we know about how these planets form? And the other one said, they form quickly the closer they are to the sun. If they're closer to the sun, how quick can they form? Let's forget about our solar system, but let's take the seeds that we had in our model that then accreted material that created the planets, but move them inward. And so that's what they did. They all went home and ran a computer model. And this now is called the Nice model. After the conference, they started all these giant planets interior to where Saturn is, okay? So Jupiter moved in, Saturn, Uranus, and Neptune all moved inward, and they started their cores. And they created the planets quite quickly. So yes, they could create a solar system that sort of looked like ours, but didn't have the distance right, okay? But here's the startling thing that came from their analysis. Now, on the left is looking down in their computer models where you see the orbits of Jupiter, Saturn, Uranus, and Neptune, and you see the debris field of smaller bodies, icy bodies that are formed, and they let it run. After they formed these planets, they were already set up to run the whole model after 4 billion years, even though you could form them in the first 10 million years. So here's what happened. After 880 million years, gravitational perturbations from Jupiter threw the outer planets to positions they are today. The debris field moved inward and bombarded everything into the inner part of the solar system. Mercury, the Moon, Earth, Mars, Venus, everything gets bombarded. And that's what the Apollo rocks told us. So now we have computer models that verify aspects of data that we obtained from the Apollos on how this solar system was bombarded early on. And so now the theory goes that as the solar system was initially created, the interaction between Jupiter, these are called resonances, between Jupiter, Saturn, Uranus, and Neptune, after about 880 million years, pushed Jupiter inward, but Saturn, Uranus, and Neptune went outward. This caused all this debris that hadn't been swept up by the planets yet to move inward and bombarded us. We have no record of that on Earth. That record is on the moon. And we now are excited to learn about that and know where to go on the moon to verify that that indeed is what happened. This is a really exciting time in planetary dynamics because when we look at exoplanets, we see there are huge Jupiters orbiting stars in orbits that they could not have possibly been created in. Huge elliptical orbits that end up very close to that sun and very far away during its travel. This elliptical orbit is not how planets are created. They're created in a big disk that swirls around the star and then accumulated in nearly circular orbits or slightly elliptical orbits, but not highly elliptical orbits. It tells us two planets fought it out. One was thrown inward and the other one thrown outward. We now know from this analysis how these giant planets end up close to the suns. And we're making huge strides in looking for planets like the Earth, or at least Earth-sized, in the right locations, and the conditions that it takes to enable those planets to perhaps have life. Another fantastic discovery only in the last few years about the moon starts in the North and South Pole. These are two images. One is the average illumination that's on the left, and the other is the temperature of the South Pole. Now, for us to be able to do this, we have to watch the moon for an entire month. So that, half the moon, and when we look at the South Pole or the North Pole, is dark, and the other half is light. That moves as the moon orbits the Earth, as we talked about before. And so when we put a month's worth of data in, we can see after a month where the sun illuminates the surface. And we find areas, impact areas, huge impact areas, where the sun don't shine. And then we look at the temperature, and we see those are some of the coldest places in the solar system. Now comes the exciting set of measurements. We have sensed that in these cold regions, there's trapped water. Now it's in ice form, it's not in liquid form, but in these permanently trapped regions, we see an enormous amount of water. This is a game changer because we can use water to drink, to break apart, breathe, to break apart, and create rocket fuel. And we don't have to carry it to the moon. It's there as a reservoir. And oh, by the way, teasing out the water on the moon to get those products is exactly what we will do on Mars. We will use the resources on Mars to live, work, and return. And so the processes that we do and work on the moon and pioneer on the moon enable us to go to Mars. So this is really a significant discovery that this permanently trapped water is available to us if we go to the right spot. In fact, the current estimate is it's anywhere between 100 to 200 million tons of water. And then just a matter of a few months ago, we found a new process. We've analyzed data from the LADEE spacecraft, and LADEE sees water being emitted from the moon. And this occurs over certain spikes in time. And you can see that these spikes here over time are when this water is detected by an orbiting satellite. They match perfectly meteor showers. Meteor showers are material that's left in orbit, a full orbit, of a comet, a former comet, leaving debris around, and that we fly through that former comet, and those bits and pieces of material impact the Earth. We all go out at night and see a variety of meteor showers. There's several that we see regularly, Perseids, Leonids, etc. And they match, of course, the time, because the moon moves through those two, of impacts on the moon liberating water underneath the surface. So the top surface layer may be a matter of a handful of centimeters, but certainly 10 centimeters down has water, but the top layers are desiccated, no water. We see that when we brought back the Apollo rocks. We thought the moon was bone dry, but we then didn't go down that deep, except for cores that we did that we haven't touched until this year. We're starting now to open these cores and look at them, and we'll get an understanding as to these kind of volatiles, like water, at depth in the moon. And so what this means the moon has a water cycle. So, I've only talked about a couple things. One of the reasons we want to go back to the moon is really all about establishing the period of giant planet migration, how the solar system was formed. Really get down to understanding the chronology of the solar system and how it was formed, because we can age date the events that occurred. That's the moon's witness plate to everything. We want to be able to look at the solar wind impact to the moon far side. That solar wind, the history of the activity of the sun, is on the surface of the moon, embedded in that far side. And we want to see how active that's been. Indeed, there are other things we can do, such as build radio telescopes using the far side of the moon as the quiet place that we then can look out into the universe at wavelengths we can't do today from Earth. And every time we do that, we discover new things in the cosmos. Now, I've only talked about a few of these things, but indeed, this is transformational science in terms of going back, or rather forward, to the moon. Most recently, NASA's been given a challenge. This is called Space Directive 1, is to go forward to the moon, develop systems and capabilities in partnership with commercial and international spacefaring groups, and then go on to Mars, and do that in a sustainable way. That means building infrastructure and capability and reuse the systems that we build. This is completely different than what we did in the Apollo era, where it was one nation, the United States, and the Soviet Union going after the moon as an object for which all resources were dedicated from each of these nations. Now we want to do it together. In fact, the administration has charged NASA with making this challenge come true, and that is, have the first woman and the next man step on the south pole of the moon by 2024. And we're up to the challenge. Okay? And that involves the world. It's not just NASA. It involves the world. NASA has a plan, a suite of things that we're going to do. And one of the major things in terms of being able to have a variety of landers and tease out some of the science that we talked about Also, in an ever-increasing capability, build a system called the Gateway at the moon, leading eventually to having humans step on the surface of the moon on the South Pole. South Pole, once again, has this enormous resource of water that we want to learn how to tap and get into. So in fact, this large system that we're building that facilitates this is called the Gateway. This will start out with a propulsion module. ESA is interested in building a habitat module. Canada wants to provide a Canadian arm. This will be the place where samples will go up to and be received after being acquired from the lunar surface, and that astronauts will come and go from this habitat. Manage and manipulate experiments on the surface, and then also move into a vehicle that then will go down to the surface and land on the moon. And of course, the orbit of the Gateway is around the moon. This enables us to have complete access to the moon at any latitude, and in particular, from the far side of the moon. It'll enable us to be able to send experiments and acquire data from that far side and begin to learn much more about the moon and, of course, the origin and evolution of the solar system. So when I look out and I see potentially the future of how we will use the moon, it's not just for science and exploration. There are many resources that are there. We're finding large areas on the moon that have platinum group metals. These are platinum and palladium and iridium, a whole series of important metals that don't rust, that have all kinds of applications that we use here on Earth extensively. But in the next 50 years, we'll mine that out. And by 250 years from now, it will be completely gone from the mines on Earth, and the only place to go and get new material will be on the moon. So the moon indeed has all kinds of resources for us and enables us for a fuel dump with the water supplies that we can use, a depot there, and also the mining and manufacturing that can be done. So in closing, what I'd like to do is play a little music with a little moon in the background that hopefully will give you appreciation for how beautiful this moon is. Thank you very much.